welcome to the deep dive. Today, we are plunging into the fascinating world of electrostatics.
That's right.
We've got a stack of sources here, basically a collection of summaries, definitions, laws, worked examples, stuff straight out of grade 11 and 12 physics.
Exactly. Think of it as a really focused look at static electricity. Our mission, really, is to unpack all this, pull out the absolute must-knows, and really get a handle on the fundamental principles. Static charges, the forces between them, the fields they create.
And it's not just dry textbook stuff, is it? Understanding these ideas helps explain, everything from that annoying shock you get from a doorknob to how, printers and air purifiers actually work. Okay, let's dive in.
Let's start with the very basics. What is electric charge? At the atomic level, it's all about protons and electrons. Protons have a positive charge, electrons have a negative one.
So a neutral object is just balanced.
Exactly. The net charge adds up to 0. Now, the unit we use to measure charge is the coulomb, symbol C. But here's the thing. A coulomb is actually a huge amount of charge in everyday life.
Huge? How huge?
Well, to give you some perspective, one single coulomb represents about 6.25 times 10 to the power of 18 elementary charges.
Wow. Okay, that's an absolutely massive number.
Yeah.
So it makes sense then that for static cling or typical physics problems, we're dealing with much, much smaller amounts.
Precisely.
Yeah,
you'll often see charges measured in microcoulombs, that's C, or 10 to the minus 6 coulombs, or nanocoulombs NC, 10 to the minus 9. And even picocoulombs, PC, which is 10 to the minus 12 coulombs. These are much more common practical units.
Okay, and is there a smallest possible bit of charge, a fundamental unit?
Yes, absolutely. It's called the elementary charge. We usually write it as E, or sometimes Ki. And that's the magnitude of the charge on a single electron, which is negative, or a single proton, which is positive. Its value is roughly 1.6 times 10 to the minus 19 coulombs. So an electron's charge is E, a proton's is plus E.
Minus 19? Tiny.
Very tiny. And this leads us to a really fundamental principle, charge quantization.
Charge quantization. Okay, what does that actually mean practically?
It means that any charge you ever find on any object is always going to be a whole number multiple of this elementary charge. You just can't have half an electron's charge floating around on its own.
Okay, so charge comes in distinct packets, like little building blocks. It's not a continuous fluid.
Exactly. It's granular or quantized. It's a key insight, showing the sort of graininess at the quantum level.
Makes sense. So how do things actually get charged then, if charge is conserved?
It's mainly about the movement of electrons. Remember, protons are usually stuck in the nucleus, so objects get charged when electrons are transferred from one thing to another.
Like rubbing a balloon on your hair.
That's a classic example. That's charging by contact, specifically friction. Electrons literally get scraped off one surface onto the other.
Okay.
Our sources also mention polarization or induction. That's where you bring a charged object near a neutral one, and it causes the charges within the neutral object to shift around, to separate, without actually touching.
Right, I've seen that, where a charged rod makes little bits of paper jump up to it even before contact.
Exactly. And if you want to detect if something has a charge, and maybe even what kind of charge.
How do you do that?
Well, a simple tool is the electroscope. It's got these thin metal leaves, usually gold or aluminum. When you transfer charge to it, the leaves both get the same type of charge, and since, charges repel, they push apart. The more charge, the further apart they go.
Neat. And you can tell positive from negative.
You can, with a bit more care. If you know the charge on an object you bring near a charged electroscope, you can see if the leaves move further apart or closer together and deduce the sign.
Okay, cool. So we know what charge is, how things get charged. Let's talk about that conservation rule again. The law of conservation of charge.
Right. This is super important. It basically says, in any isolated system, the total net charge stays the same, no matter what physical process happens inside.
Isolated meaning nothing gets in or out.
Exactly. You can move charge around within the system, between objects that touch, but the overall sum of positive and negative charge doesn't change.
So, like your example earlier, two charged spheres touching.
Perfect example. When they touch, electrons can move between them. They'll naturally flow from the place where there's an excess of them, the more negative sphere, to the place where there's a deficit, the less negative or more positive sphere.
Until when?
Well, if the spheres are identical, same size, same material, the electrons redistribute until the charge is spread evenly. They end up with the same charge once you separate them again.
Okay, let's use the source's numbers. Say sphere A starts at +5 coulombs, and sphere B starts at -7 coulombs. They're identical.
Right. So before they touch, the total charge in the system is just the sum, +5C plus -7C equals negative coulombs total.
Okay, -2C total. So conservation says after they touch and separate, the total charge must still be -C.
Correct. And since they're identical and share equally,
Each one gets half. So -1 coulomb on sphere A and -1 coulomb on sphere B.
exactly. The charge redistributed, but the total amount stayed constant.
Do we figure out how many actual electrons made the move?
We can. Look at sphere A. It went from +5C down to -1C. That's a change, delta Q, of -6 coulombs.
Right.
It gained 6 coulombs worth of negative charge.
Okay, yeah.
So the number of electrons transferred, let's call it N, is just that total charge transferred. 6 coulombs divided by the charge on one single electron, which is that elementary charge E. 1.6 by 10, 19 coulombs per electron.
So 6 divided by 1.6 times 10 to the -19. That's...
It's a huge number again. It comes out to 3.75 times 10 to the power of 19 electrons.
Wow. Almost 4 times 10 to the 19 electrons flowed from sphere B over to sphere A just to change its charge by 6 coulombs.
Yeah, it really shows you the scale we're talking about. A massive number of electrons make up even seemingly small amounts of net charge.
Okay, so charges exist, they're conserved, they can move. What happens when they're just sitting near each other? The forces, right? That brings us to Coulomb's law.
Yes, Coulomb's law. This describes the force, the push or pull between 2 point charges.
Point charges meaning like really small charged objects.
Yeah, small enough that we can treat them as points, or spheres where the charge is uniform and we measure distance from their centers. Coulomb's law says the magnitude of this force is directly proportional to the product of the charges.
So bigger charges mean bigger force.
Right. And inversely proportional to the square of the distance between them.
Ah, the inverse square law again. Like gravity.
Exactly like gravity in form. The formula is F equals K times Q1 times Q2, all divided by R squared.
F AQ1, Q1 EQ 2R log. Let's break that down. F is the force.
Yep, the electrostatic force, measured in newtons. Q1 and Q2 are the magnitudes of the two charges, in coulombs.
Magnitudes.
Mm.
So you ignore the plus or minus sign when you plug them in.
Crucially, yes. For calculating the size of the force, you use the positive values of Q1 and Q2. That's a really important point from the sources.
Okay, so the formula gives the strength. How do you know if it's a push or a pull?
That's where the signs come back in. You look at the original charges, like charges repel, so the force pushes them apart, unlike charges attract, so the force pulls them together. Force is a vector, remember?
Right, magnitude and direction.
Exactly. And R in the formula is the distance between the centers of the charges in meters. And K is Coulomb's constant.
Which is that number, 9 times 10 to the 9.
Yep, 9 by 109. And the units are Newton meters squared per Coulomb squared, so it all works out to give force in newtons.
Okay, let's talk about those proportionalities again, especially the distance one.
Sure. So F is proportional to Q1 times Q2. Double one charge, force doubles. Double both charges.
Force quadruples, 2 times 2.
Right. But the distance part, F proportional to 1 over R squared, that's where things get dramatic. Double the distance.
Force becomes 1/4. 2 squared is 4, 1 over 4.
Perfect. Halve the distance.
Force becomes 4 times stronger. Half squared is 1/4, 1 over 1/4 is 4.
Exactly. And the sources mention if you reduce the distance to 1/3,
then the force is 9 times greater. Wow. Distance is a huge lever here.
It really is. The electrostatic force drops off very quickly as things get further apart. It's incredibly sensitive to distance. That inverse square relationship is probably the biggest takeaway from Coulomb's law.
You can see why it's so similar in form to gravity, which also acts over vast distances but weakens in the same way.
Though gravity only pulls, it's always attractive and depends on mass. Electrostatics depends on charge and can push or pull.
Okay, let's try a calculation for the sources. 2 small metal spheres, A and B. A has -4 picocoulombs, so -4 by 10 12C. B has -3 picocoulombs, -3 by 10 12C, and they're 5 centimeters apart.
Okay, so first, direction, they're both negative, like charges.
Repel. The force pushes them apart.
Right. Now for the magnitude. F equal is KQ1, Q2 over 5. We need magnitudes of Q1 and Q2. So 4 by 10, 12C and 3 by 10, 12C. Distance Y needs to be in meters, so 5 centimeters is 0.05 meters.
Got it. So F 9 by 109 times 4 by 10 to 12 times 3 by 10 to 12, all divided by 0.05 squared. Plugging that in.
You get a force magnitude of 4.32 by 1011 newtons. Tiny force, but measurable.
Okay, 4.32 by 1011 N, repulsive. Now, the source example does something interesting. What happens if these identical spheres touch and then separate again?
Ah, okay. Well, we use conservation of charge again. Total charge is -4 pc plus -3 pc -7 pc. Since they're identical, they share this equally after touching.
So each one ends up with half of -7 pc, which is -3.5 picocoulombs.
Exactly. Now let's recalculate the force between them at the same 5-centimeter distance, but now each sphere has -3.5 pc.
Okay, FT, K 3.5 by 10 to 12. 3.5 by 10, 12. Why don't I get 4 or 5 minutes?
Right. Plugging that in gives 4.41 by 1011 newtons.
So the force magnitude actually increased slightly in this case, from 4.32 to 4.41 times 1011 N. And it's still repulsive since both are still negative.
Yeah, it's interesting how redistributing the charge changed the interaction force, even though the total charge was conserved. It really highlights how the specific charge values matter. The product Q1, Q2 changed.
That's a great illustration. And if you had, say, 3 charges, how do you find the force on one of them?
You'd use Coulomb's law for each pair involving that charge. So find the force from charge 2 on charge 1, find the force from charge 3 on charge 1, and then you add those forces together as vectors. Remember, direction matters.
Vector addition, right. Okay, so that's the direct push and pull. But you mentioned charges also create something in the space around them.
Yes, the electric field.
What exactly is an electric field? It sounds a bit abstract.
It is a bit abstract, yeah. Think of it like this. A charge modifies the space around itself. It creates a condition, an influence. The electric field is that region of influence. If you place another charge into that region, it will feel a force because of the field.
So the field is there even if there's no second charge to feel it.
Exactly. It's a property of the space caused by the source charge.
And we draw pictures of this using electric field lines.
We do. They're a way to visualize these invisible fields. And the key convention is, an electric field line shows the direction of the force that a tiny positive test charge would experience if you placed it right there.
Always a positive test charge.
Always positive, by convention. So around an isolated positive charge, the field lines point radially outwards because a positive test charge would be repelled, pushed away.
And around a negative charge, they'd point radially inwards because the positive test charge would be attracted.
Precisely. And the sources list some important rules for these lines. They're imaginary 3D constructs.
Right, just a model.
They start on positive charges and end on negative charges. They always hit the surface of a conductor perpendicularly. And crucially, they never cross each other.
Why not?
Because if they crossed, it would mean the field had 2 different directions at the same point. And a charge can only be pushed in one net direction at any single point.
Ah, makes sense. One force, one direction.
Right. And one more thing. How close together the lines are tells you how strong the field is. Densely packed lines mean a strong field. Spread out lines mean a weaker field.
The pictures in the sources show this. Like, between 2 positive charges, the lines look like they're pushing away from each other in the middle.
There's a repulsion, yeah.
And between a positive and a negative charge, the lines curve nicely from the positive towards the negative.
Showing the attraction. And there's another really important pattern. The field between 2 large, flat, oppositely charged parallel plates.
Oh yeah, that looked different. The lines were straight and evenly spaced.
Exactly. Between the plates, away from the edges, the field lines are parallel, equally spaced, and perpendicular to the plates. This represents a uniform electric field.
Uniform meaning?
Meaning the electric field has the same strength and the same direction at every point in that region. This is very different from the field around a point charge, which gets weaker as you move away. That's a non-uniform field.
Okay, uniform versus non-uniform. So how do we actually measure or calculate the strength of the field? Put a number on it.
We call it electric field strength, usually symbol E, and its definition is the force experienced per unit positive charge placed at that point.
Force per unit charge. So E equals FQ, where F is the force on a test charge Q.
That's the defining equation, yes. E equals FQ. The units would be newtons per coulomb. And C.
Okay. And is there a formula to calculate E directly from the charge creating the field?
Yes. For the field created by a single point charge Q at a distance r away, the magnitude of the electric field strength is E equals KQR1. Notice it's r squared again, another inverse square relationship.
Ah, so the field strength also drops off like 1R1.
Yeah.
And Q is the charge making the field.
Correct. Q is the source charge causing the field. And Q in the other formula, EFQ, is the test charge experiencing the force within that field. It's important to keep those straight.
Got it. And again, for E equal KQR1, you use the magnitude of Q, ignoring the sign, to get the field strength.
Yes. The sign of Q tells you the direction of E field points away from positive Q towards negative Q.
And the direction of E is the direction a positive test charge would move.
Exactly. So if you put a positive charge Q in a field E, the force on it, FQE, is in the same direction as E. But if you put a negative charge Q in the field, the force FQE is in the opposite direction to E.
Okay, that's a key difference. Positive charges go with the field lines, negative charges go against them.
Precisely. And this ties back to motion. Remember FMA. Since FQE, the acceleration is a QE.
Ah, so in that uniform field between the plates where E is constant.
The force FQE is constant, and so the acceleration A is also constant. Charged particles move with constant acceleration there, like projectile motion under gravity.
But around a point charge, the field E is non-uniform. It changes with distance.
So the force changes and the acceleration changes too. The motion is more complex. That uniform versus non-uniform distinction is really useful.
Definitely. And like with forces, can you find the net electric field at a point if there are multiple charges around?
Yep, same principle. You calculate the electric field vector, magnitude EKQR for it in direction, caused by each source charge at that specific point in space. Then you add all those individual electric field vectors together using vector addition.
Okay, let's look at the source example for that. Find the net field at point P. There's a charge, Q1 equals 14 microcoulombs, and Q2 equals plus 20 microcoulombs. They're 3 meters apart on a line, and point P is on the same line, 2 meters away from Q2.
Okay, first visualize. Q1 negative on the left, Q2 positive on the right, 3 meters apart. P is between them 2 meters from Q2, which means it must be 1 meter from Q1.
Right. Now the field E1 at P due to Q1. Q1 is negative, so E1 points towards Q1 to the left. Its magnitude is KQ1, 1 meter's market.
And the field E2 at P due to Q2. Q2 is positive, so E2 points away from Q2, also to the left. Its magnitude is KQ2, 2 meters left.
Correct. So at point P, both fields happen to point in the same direction, left.
Yep. So to find the net field E net at P, we just calculate the magnitudes of E1 and E2 using the formula. And since they point the same way, we simply add those magnitudes together. The direction of E net will be to the left.
If P had been somewhere else, say, to the right of Q2, then E1 would point left towards Q1 and E2 would point right away from Q2, and we'd have to subtract the magnitudes.
Exactly. Vector addition is absolutely key for both net force and net field calculations.
Okay, this is making sense. We've gone from charge to force to this idea of an electric field mediating the force. Where does this actually, show up? What are the applications?
Good question. Static electricity isn't just, like you said, shocks and cling wrap. It's used in some really clever ways. The sources list several.
Like what?
Well, electrophotography is a huge one. That's the core tech in laser printers and photocopiers.
No.
Basically, they use light to create a pattern of static charge on a drum. Then tiny charged plastic particles, the toner, are attracted only to the charged areas. That pattern then gets transferred to paper and fused on. It's all about controlling electrostatic forces.
Wow, okay. That's pretty sophisticated. What else?
Van de Graaff generators, those big metal spheres you sometimes see in science museums that make your hair stand on end. They use a moving belt to continuously transfer charge, building up a really high voltage, a big static charge, for experiments or demonstrations.
Right.
And then there are things like electrostatic smoke precipitators, used in factories or power plants. They charge up the smoke particles and then use electric fields to pull them out of the exhaust gas onto collection plates.
Cleaning the air using static electricity.
Yep. Similar idea in some home electrostatic air cleaners, too. Charging dust and pollen and collecting it.
So all these things are basically just manipulating charges and using the attraction and repulsion forces we've been talking about.
Exactly. They're leveraging Coulomb's law and the concept of electric fields in practical ways. Charging by contact or induction, creating fields, making charged things move where you want them to.
Okay. So wrapping this up, we've really gone from the absolute basics, the idea of positive and negative charge at the atomic level, through the rules like conservation of charge, how charges interact via Coulomb's force, how they create these electric fields, all the way to seeing how these fundamental ideas power technologies we use every day, like printers and air filters.
It's quite a journey, isn't it? What's really fascinating, I think, is how these concepts that seem quite simple, like charges repel, opposites attract, scale up to explain so much, from atomic interactions to complex machines.
Absolutely. Static electricity often just seems like a nuisance, doesn't it? That clingy sock, the dust on your TV screen getting zapped.
Yeah, mostly annoying.
But when you dig into it, it's actually the surface effect of these incredibly powerful fundamental forces that literally hold matter together and shape our technological world.
That's a great way to put it. So maybe a final thought for you listening. Next time peel off some plastic wrap and it crackles and sticks, or you see dust clinging weirdly to something,
Yeah.
just take a second to picture those invisible forces, those electric fields extending out, described by Coulomb's law. It's a little window into the unseen world of electrostatics that's operating all around us all the time.
A great thought to end on. Thanks for joining us for this deep dive into electrostatics.